Hi, this is Shully Physics Kinematics episode on deriving motion equations. Whoa, deriving. Yeah, we're gonna be deriving here today. But before we get deriving, you might recall that the average velocity from our last session is a change in position over time. Okay, so that change, whenever you see change, it's a final minus an initial every single time. So what we're talking about here is a final position minus a starting position. In physics, we might say xf or x naught or x zero. Naught is an old word meaning nothing, all for naught. So x naught. And change in time would then also be t final minus t initial. Now, one thing about time is usually when you're taking a time or timing a activity like sports or a race, what is the starting time? 0. So oftentimes we might simplify this simply to a single t, like the elapsed time, the time it takes for the event to take place, to go from the start to the finish. But do keep in mind occasionally there may be a time setting where we're not starting at 0. If that's the case, delta t would have to include a final minus initial. If you think about the final minus initial position, position in the beginning of an event is also often 0. So we're just trying to take a total change of position divided by total change in time. And that can take any forms. So if it's a bus on a trip and the bus is traveling at a certain 60 miles per hour for the first hour and a half, then it stops for 20 minutes to let the people go and do their thing at a restaurant, whatever that might be, and then they get back on the bus and travel on more local roads at 40 miles per hour for the next 45 minutes before they get to their destination. That total distance traveled divided by the total time would include the first segment of travel, would include the time while the bus is stopped, would include the time when it was moving at a slower speed. So that total distance, if they go 100 miles in the first segment, they stop and they travel another 50 miles, then that total time might be 150 miles. And the time it might have taken them, I forget what I said, 1.5 hours plus 45 minutes would be 2.25 hours. So we would get a value out of that in miles per hour. Okay, that would be an average speed. So I'll take a minute to bring up my calculator. There it is. And we take 150 divided by 2.25 hours. And so the average speed might be 66.7, we'll just say 67 miles per hour. Wow, that's a fast moving bus. Okay, so I guess it's going faster during a portion and slower. Oh, wait a second. It stopped for 20 minutes. Isn't that going to bring our average speed down? So this time wasn't, the total time wasn't 2.25 hours. I missed a little bit here. It did travel 150 miles, but it didn't stay at that top speed for that entire time. So 20 minutes is 1/3 of an hour. So I'm going to add a third to that. Add a 0.33 to that would be 2.58 hours. So our average speed, average velocity is going to be a little bit less than that. 2.58 hours, 58 miles per hour. Do you see how that stop in the middle reduced the average velocity? Okay, so sometimes average velocity when you're looking at an entire trip is pertinent. Next, let's look at the average acceleration. What does average acceleration look like and what kind of context might that be in? Well, this is a change in velocity over time, over a change in time. And again, we're going to see a final change minus an initial. And again, I'm just going to put a t here because our beginning of our change in velocity that causes the acceleration is probably starting at time t equals 0. So that t0, the t naught, is just a 0 here also. But now with acceleration, it is more important that we keep the finals and the initials and the velocities here. You see up top, we kind of just assumed that the starting position of the bus was 0, was at the beginning. So oftentimes you can just take a distance over time to find an average velocity, and you're not really thinking too much about the starting position. That does become important when you have two objects in motion and you're trying to get a relative motion to one another. You should have a non-zero starting point for at least one of those objects. But for acceleration, it is very common. Most of the time, the initial velocity may not be zero. Yeah, you might have a car at a stoplight where the initial velocity is zero and it speeds up from there. But what if it's slowing down? What if you're driving at 40 miles per hour and you see a deer ahead and you can just slow down to 20 miles per hour to allow that deer to pass? Well, in that case, instead of miles per hour, let's start using meters and seconds. So let's say you're traveling at a whopping 40 miles per hour to start, and you need to slow down to 20. Do you see what happened there? The final is 20. The initial is 40. And let's say you do that in 5 seconds. Okay, it's not a suicidal deer. You know, they gave you lots of room to slow down there. So this is 20 meters per second is the final speed, final velocity, and you're starting at 40 meters per second. So what do we get for that acceleration, that average acceleration? You get a negative 20 meters per second over 5 seconds. So your average acceleration would be a negative 4 meters per second squared. And what this means is you're slowing down in the forward direction by 4 meters per second every second you apply the brakes. So if you do start at 40, then after 1 second of slowing down, you're now going 36. After 2 seconds, you're going 32. After 3 seconds, you're going 28 meters per second. After 4 seconds, you're going to 24. And after 5 seconds, you're down to 20 meters per second. That's how that acceleration works. Get an average acceleration of negative 4 meters per second squared. Now what really happens if you've ever driven a car is you probably see that deer and you slam on the brakes quite a bit. So your initial acceleration may have actually been much more than negative 4. It could be like negative 12. So everyone gets jerked forward when there's that change in acceleration. By the way, that is a physical quantity. It's the average rate of acceleration change. It's called jerk. But we're not going there in this class. So you might get jerked ahead at negative 12 meters per second, but then you let off that brake a little bit. Once you see it's your car's in control and you're not going to hit that deer, you might decrease that acceleration down to like negative 1 meter per second squared by the end of that time. But the average acceleration would still be negative 4. It would be the same as holding down that brake and having a constant acceleration of negative 4 meters per second squared for the entire 5 seconds. Where in reality, it's probably a lot different. There's different changes, different amounts of acceleration throughout that period. So these are couple of examples of using average velocity and average acceleration. So what about instantaneous velocity? Instantaneous. You might recall we have to use that derivative form. Instead of delta x over delta t, what we're looking at is a small change in position that occurs over a small change in time. It's still a rate. It's still a ratio of change in position to time. Okay, but we're going to get a very small look at it, which brings it down to an instant in time. So in that bus trip, or in that while we're slowing down to avoid hitting the deer, what would our instantaneous velocity be at any moment throughout? Well, with that, you kind of need to know a little bit about the position function. So with this, you are often starting with some kind of x of t function, or maybe it's a up and down direction. It could be y of t, a change in position in the y direction, a vertical motion. Okay, so if you do have some kind of expression that relates the motion of an object, let's say 20 plus 5t minus, I'm just making up something here, 3t squared. Okay, so if this is describing your motion, what does that look like? Well, if you can imagine it, if you've done some graphing of equations in your math classes, this is a quadratic that'll have a parabola that's kind of dipping down, but it is starting at a y equals 20, and it may actually go up a little bit before it dips down. So if you plot that out, you'll probably get a plot that starts up at about 20 on the y-axis, and it'll go up and then down, dip down, sort of like that. So there might be a speeding up at first, I'm sorry, there should be a forward motion at first where x's increase, and then they should decrease back towards 0. But if you do start with this, what is the velocity at any moment in time? We can take d of that x, that position function, dt. So we're taking the derivative of all this. What's the derivative of 20? It's 0. What's the derivative of 5t? Well, that's t to the first power. The derivative decreases that exponent by 1 to t to the 0 power. So we end up with 5. Okay? And then minus 3 times 2. Remember, take the derivative. We're going to multiply by that n. So 3 times 2, t to the 1 power. So out of this, we would get 5 minus 6t. And look at that. We can plug in any value for time and figure out what the velocity, what that instantaneous velocity is. All right, so we'd have a v of t function now that's equal to 5 minus 6t. All right, move this down a little bit. All right, so what do we do with this? Well, if at 1 second, the velocity would be 5 minus 6. It would be a negative. At 2 seconds, it would be 5 minus 12. That would be negative 7 meters per second. But at a half second, all right, just after this motion started, at a half second, it would be 5 minus 3. So it would be a positive 2 meters per second. This does show you that the motion is progressing forward in the positive direction at first, but then it'll become negative as time ticks up higher and higher and higher. That would give us a curve that looks something like this. If this is x position, not the x-axis, but the x as position, and t is along the x-axis being time. Okay? All right, so that's what that position time function would look like. Next, what can we do with velocity? Well, instantaneous acceleration. Is this thing accelerating? If the velocity changes, that's the definition of acceleration. If the velocity is changing, there is a non-zero acceleration. So this should be giving us a non-zero acceleration value. Let's check it out. Acceleration that's instantaneous acceleration is dv dt, the derivative of the velocity function. So if we take d of that vt function with respect to time, then we're going to take the derivative of this 5 minus 6t function. Derivative of 5 is 0. Derivative of negative 6t is negative 6t to the 0 power, which is negative 6. So this acceleration is a constant. At 1 second, it's going to be negative 6. At 2 seconds, it's going to be negative 6. At 18 seconds, it's going to be negative 6 meters per second squared. So this object is not just slowing down. It's going to slow down at first. It's going to get slower. But do you notice at the top here, there is a point where the velocity should be 0, where the object stops moving forward and starts moving backward. So this isn't just slowing down. Here it slows. But here it gets faster in the negative direction. So it's not always good to say, oh, there's a negative acceleration of slowing down. It's best to say this object is undergoing a negative acceleration, or its velocities are becoming more negative. If it's starting with a positive velocity, more negative means that positiveness is going to decrease. So it slows at first. Then at some moment, at some instant, it'll stop. Isn't there a value of t where velocity is 0 here? Is that possible? Can we solve for t? Yeah. That would be a negative 5 divided by negative 6, which is 5/6 seconds. Okay? There's a decimal associated with that. So at 5/6 of a second, this object's going to be stopped. But then it's going to start moving in that negative direction. It's going to turn around and go backwards from the direction it originally was starting at. Okay? So this is how you handle finding velocity and acceleration from a displacement function. But hey, what if you're starting with an acceleration? What if A of t is a function? What if it's 2t to start? What then would be the velocity and the displacement function? What would they look like? Well, since velocity is a change in position and acceleration is a change in velocity, we take the derivative to go this way. All right? We have to take the derivative each time to go that way. And guess what? If we wanted to go this way, from left to right there, we need to take the integral. We got to integrate. Okay? If we're going this way, derivative that way, integrate that way. Make that little chart. That might be helpful right now if in all this. Like a problem might be thrown at you. Here's a velocity function. Find its displacement and acceleration. You don't want to get these mixed up. But just, I think the first thing I think about is, well, what is v and relative to acceleration relative to x? Well, acceleration is the change in velocity, so that's the derivative. So to go to x, to go to the displacement, I gotta think, oh, velocity is the change in position, so I have to integrate to get the position from the velocity function. All right, so if we're starting out with an a of t equals 2t. All right, this is how the integration bit works. You make a definition. You think, okay, a instantaneous acceleration is equal to dv dt, which is 2t. Okay, so a of t is defined as this function. Acceleration as a function of time is 2t, but acceleration is also the rate of change in velocity, dv dt. So if this is your first year in calculus and you're starting up with this, here's how this notation works really well. You treat these dv's and dt's, that you never separate the dv, that stays together, and the dt, that always stays together, but treat them as something that you can work with algebraically. So we can multiply both sides by dt. And dt divided by dt over here cancels. So we get left with an expression, dv, a small change in velocity, that's what that means, a small change in velocity equals 2t times a small change in time. You see that it's a product there. And now we're ready to sum up all those little changes and all those little changes in velocity that are associated with a small change in time. This thing is what we're looking at, instants in time, little pieces. Okay, if we plotted something like this, on an acceleration time graph, all right, this would be a linear function. It would look something like this. 2t is a little bit, more steep than a straight diagonal. Okay, so this is a of t equals 2t. Looks like that. All right. So if we plotted this out, what we're really looking at is an instant, a really small piece. What is this little piece here? And we're multiplying a, which is 2t, by a small little change in time, a little dt here. All right, and that'll give us a little slice, a piece of an area. Remember, this a is equal to 2t, so that gives us like the side of a rectangle, this side, and the little dt is the base of that rectangle, if you can approximate this as a rectangle. All right, but what you might do in the end is actually go from like 0 to 5 seconds, so you could look at the whole area underneath that curve there. But in essence, what we're going to do is sum up all the little dv's, which is the sum of the product of a, which is 2t, times dt. All right, so we're just setting up the integration here. I made a lot of words in that last moment to describe something pretty like the next step that's simple. We're just putting this little integration sign in front of both. So integral of dv is v. And over here, integral of 2t dt is 2, keep that coefficient up front, t to the n plus 1, and the n is 1 to start with, so n plus 1 is 2, divided by 2. So t to the n plus 1 divided by n plus 1. That's the power rule for integration. I'm going to redo that squared there. All right. So out of this, oh, can't forget something here. There's a constant we can't forget about. This is an indefinite integral. There's a constant. So out of this expression, we're going to get 2 divided by 2 times t squared. Now, what does that see? If the left side of the expression is some velocity at a certain time, it's really a v of t function here, it would be t squared plus c has to be the initial condition that has the same units as v. So this, in physics, because v is a quantity here, we know that this constant has to be the initial velocity. It may start at 0, it may start at 5 meters per second, whatever it is. It may start at negative 10 meters per second, but that's the initial velocity. That's what the c stands for. Okay, c is that initial velocity. So we've come up with a function for velocity with respect to time, v0 plus t squared. All right, and so I went from an acceleration function to a velocity function, and now I'll speed this up a little bit. We have one more step here. We need to find the displacement function. So since v is the same as dx dt, and that's v0 plus t squared for my example here, I'm going to multiply both sides by dt. And that gives us dx equals v0 plus t squared dt. I'm going to drop my integral sign on both sides. We get x equals, so position at some time, equals integral of a constant dt would be v0 times t. We're going from a t to the 0 power, which is 1, that makes it invisible here, to a t to the first power, plus t squared becomes a t cubed divided by 3, and we can't forget our plus c. But in this situation, c has to have the same units as x, and it's an initial condition, so that c becomes an initial position. There's xo, can't forget it. It's usually there in these expressions. And there we have an x of t function. Let me erase this a little bit and add my x of t. There it is. All right. So this is the process. When you have a non-constant acceleration to begin with, this is the process for working through it. You can either start with a displacement function, that's what we had here, and go through and find the velocity and then the acceleration using derivatives, or you can start with an acceleration function and integrate to find velocity, integrate again to find displacement function. All right. Now, common things, common scenarios. Got a nice flashlight here. Okay. You light up my life. I will not sing again. Maybe. I'll probably edit that out. So here's a flashlight, and I drop it. Well, it didn't just coast down at a constant speed. It accelerated as it fell. I know that because if I drop it from this height, it doesn't get going very fast. If I drop it from this height, I felt a lot more pressure when it hit my hand. You can try it yourself. If you jump off just a couple of steps, no problem, you land. If you jump off 6 steps, it might hurt when you hit the ground. If you jump off 20 steps, you might really injure yourself or kill yourself that way. You're moving faster as you fall, as you accelerate. And that acceleration is rather constant. As long as there's no not a lot of air resistance, free fall acceleration is constant. So there are many situations in physics especially where acceleration is constant. So what I'm about to show you, these expressions that we're going to get are specifically when acceleration is constant. Okay, we call this constant acceleration scenarios. Okay, constant acceleration. So let's say we have an A. A is constant. Now what I'm going to do is keep this all without extra numbers. I'm not going to give you a specific example here. So we just know that A is constant, and A is equal to dv dt. So as long as A is a number like -6 or 2 or 9.8, you may recognize that if you've taken physics before. We're starting with A as a constant number, and that's very important to note. Now just like before, I'm going to multiply both sides by dt. So we get a constant A times dt on the right. So dv equals A dt. We're going to integrate, and we get a v equals at plus c. But remember, this c is an initial velocity. So we can rewrite this, v is a function of time, equals an initial velocity plus acceleration times time. If you've taken a physics class before, you may recognize this as one of the equations of motion. And by the way, v of t could be a final velocity at a certain time. And if we subtract VO on the other side and divide by the elapsed time it takes for that event to happen, look, just algebraically you rearrange this and you get change in velocity over time. So this shouldn't be like a wow moment, like, wow, I didn't know that. But as long as acceleration is constant, you will get a nice finite change in velocity that is the same rate during that entire time segment. So this is one of our equations of constant acceleration. Well, what can we do now? We've got, we also know that dx dt is equal to v, and v is equal to v naught plus at. So let's move it on from there. If we multiply both sides by dt, they go away, and we get a dx equals, forgot to integrate here, need to integrate. All right, so we integrate a constant, you get VO t. So integral of VO with respect to t, VO dt is the initial velocity times time. So again, this is a constant number. It could be like 2 meters per second or 18 miles per hour, whatever that starting velocity is. Now we integrate this. A is a constant, remember, so it stays out there. Okay, it's a coefficient. And the integral of t becomes t squared divided by 2. And again, we need to add plus c. Oh, what did I do on this side? Need to, there we go. If we integrate dx, we'll just get an x on this side. So what is the c? What is the c value? It has to have the same units as x, and it's the initial condition. So this is the initial position. Get that viewed right. There we go. So our x of t function becomes initial position, xo, plus initial velocity times time, plus, and what I'm going to do is bring out this 2 in the denominator. I'm making it 1/2 a t squared. So if you've never seen that before, if you've taken a physics class and this equation was just thrown at you upside your head, and you're like, oh, I got position function hit upside my head, then that's where it comes from. All this came from a little fact that A is constant. As long as acceleration is constant, you can use these two equations of motion to work with constant motion. There's a, do that. This is equation 1, equation 2. And finally, without any calculus needed, I'm going to give you introduce one more equation of motion that will be useful to you. And you will not have to go through this every single time. It's probably going to, if you're taking AP Physics, it's going to be on your AP Physics equation sheet. And usually any college class will have this equation given. So if you look at these two equations, just to rewrite them, we got VF, final velocity equals initial velocity plus a constant acceleration times time, and final position equals initial position plus initial velocity times time plus half constant acceleration rate times time squared. Okay, so I'm going to rewrite those as equation 1, equation 2. If we look at these two, what do they both depend on? Well, they've got initial conditions. That's not what I'm really talking about. They do depend on their initial conditions. They also depend on acceleration. That is also important to keep here. That's not changing because it's important to know the constant acceleration. That's going to be involved in all these motion equations. But you'll notice that they both are time dependent. All right. What if you just don't have time? Now you can say that with a couple different contexts. But what if you physically have not measured time, but you have measured displacement? Could we possibly know the velocity of an object if it's accelerated over a certain distance? And we don't really have a time measurement. With these two equations, we can't really solve for that. So what I'm going to do is rearrange this algebraically to solve for time. We're going to plug it in here and here. So we're going to solve a system of equations, two equations with two unknowns. These are two unique equations. This one gives us a final velocity. This one gives us a final position. So can we find velocity and position based off of, that's time independent. That's what we're going for here. So if I take equation 1 and rewrite it, VF minus V0, we're going to bring the V0 over to the other side, and we'd have to divide by A. It's supposed to be a 0 there. Divide by A. We're going to take this expression, plug it in up here. Finally arrived at it. Positive VO squared plus 2A delta X. That is our useful equation number 3. It's just a combination of equations 1 and 2, but you'll notice it is packed as a non-time dependent equation. You can use this if you don't know time. If you know the distance over which an object's accelerating, it determines its final velocity. But these equations, 1, 2, and 3, they're only good forget it. Technological constipation. These 3 equations are only good when you have constant acceleration. That is the premise, that is the assumption we started with. If you ever have a situation where acceleration is not constant, notice this one. A is dependent on time. It is changing over time. Then you can't use these equations of motion. I just warn you with that. Early starting physics students often make that mistake on a test, and you don't want to do that. So here they are, ladies and gentlemen. Your equations of motion I give you. These will become your friends, and you might be trying to memorize them now. Don't bother, because you're just going to know them later on. We're just going to use them so much. 1/2 AT squared. There they are. Doesn't matter what their number is, 1, 2, or 3. That is just the common order you see them in. But over the next few days, you're likely going to be using these equations of motion, solving for different scenarios, and getting used to using them as a tool. These are tools. You take what you have, you figure out what you don't have. And I hope this long presentation will be helpful to you in the future.